I'm going to talk about the project I've been working on for a while. It's called Iceberg, not Project Iceberg, just Iceberg, so we don't have any confusion. It's a modern table format for big data. And I say modern table format to get past the next question and sort of sneak it in there like no one even asks, why do we even need a new table format? Is there a problem with the one we have? So first of all, I'm going to try and convince you guys in this talk that there is a problem with the table format that we have and that we can do things a better way. So starting off, what are the problems with the tables that we have today? Here's what the data landscape at Netflix looks like. A lot of these are specific to us. So things like appends are actually overwrites except in Presto, and that's why we don't say write in Presto, and things like that. But there are still catches, even if you're not at Netflix, and these things don't trip you up. The trade-off between appends actually overwrite data is that there's a little tiny period of time for every Hive write where if you were to read that table during that period of time, your query is going to lie to you. And we generally don't like times when our big data queries for our big important companies that are making big decisions based on big data lie to us. So that's a bit of a problem. And then we've got all of these other issues, as you can see here. So things like, if I'm using CSV, I can rename a column. If I'm using Avro, I can rename a column, but I've got to go edit a file underneath the table to make that happen. And there are all these just little caveats and catches to the way we use our big data tables today. So what we want to do is broaden, at least at Netflix, the set of users who can access our data and make it easy for them so that tables just work the way they expect. And it's pretty simple what users expect, but I just want to go through these and sort of tell you guys how it works today and how that breaks user expectations. So users expect reliable types. And that sounds really silly. Of course they expect timestamp to give them the timestamp that they expected, you know, the one that they put into the system. But it actually doesn't work that way in a way too much of my life at Cloudera fixing the timestamp problems that I had earlier introduced. So we want reliable support for types, and we want that across every single data format that is supported in a table. We want struct, list, map support, and nested combinations of those things. And this isn't all that hard to ask, but with tables today, we don't get that. How many levels of nesting can you have in a CSV table? I don't know, I wouldn't even try it, to be honest. We also want things like schema evolution. All the time, our users run a Hive statement that says, alter table, rename column X to column Y. And that breaks their table probably more than half of the time. How crazy is that? Then we also want hidden partitioning, right? I don't want all of my big data users to have to think about the physical layout of the table that they're querying. That is a recipe for either really, really slow queries if the user just doesn't care, or you're going to get users that just hate working with your data because they have to look at how it's structured physically. They have to understand way too much about the system. So users don't expect any of those things. They also have some, I think, more broadly reasonable expectations, like queries don't lie, not even occasionally, just never lie. Changes should always be atomic, and readers and writers should always be isolated. So these are just fundamental concepts that we get from the older database world. And then I'm going to tack on two more things that I think users tend to expect, especially as we broaden the set of people that are working with our big data products. users expect databases in general to make smart choices on their behalf. None of the users I've ever worked with really enjoy tuning Parquet files. They tend to think, why am I doing this? Why don't you do this for me? And just, it's a mess. And what we end up with is no one ever tunes their Parquet files. We just get slower queries in general. The other thing is users expect to configure tables and not jobs. And what we have today is a system where jobs are configured and not tables. So if you want to set the combine limit for splits in a big data query, you do that differently in Pig, Hive, Spark, and Presto. And it's all a job level or a session level configuration variable to set this one thing that determines, very huge impacts, has a very huge impact on your performance. So that really sucks today. And basically every configuration setting that you care about is different in all of these different engines. So I think that we can do better on all 6 of these fronts. That's basically what Iceberg is attempting to do. So Iceberg is taking the table format that we know today, that we're used to, that we've not really thought about recently, and says, hey, maybe we should redesign that so things like atomicity and snapshot isolation are baked into how we work with data. So Iceberg tables are snapshot-based. Every write creates a brand new snapshot of the table state. And I know that sounds crazy, like we're never going to make that happen performance-wise. The details of that we can go into later. But every write is atomic, either completely done and visible, or it errors out and is not there at all. This is done at a file level, not a partition level. That's how we got appends are actually overwrites in my earlier slide. And this also allows us simple built-in change detection for things like materialized views. So with this, we can do a lot more with our tables. Oh, and the really nice thing is if we have snapshot-based tables, if we can trust our writes, so we don't have this small period of time every time we write to a table when the table might just return bogus data for a query, then we can write to our tables more. We trust this operation, so we can go back and fix things in the table. We could go compact small files. We can repartition to a new layout. We can do a lot of things that we cannot do today because we think the more times I write to this table, the more likely it is that it's going to lie to someone. The other contribution of Iceberg as a project is that it's a table format library. So it's a common implementation that we're baking into multiple systems. It's a library that we're putting into Spark through the data source v2 API. We have a Presto pull request out, and it's something that we can even access table data directly without going and listing a million paths in S3 after you hit some random metastore endpoint. So this gives us a great vantage point to do things like fixing the job level operations that I was talking about earlier, where every time I want to change a configuration, I have to go look up what that configuration is in whatever engine I'm using. Well, here we're doing all configuration through the table level. That allows me to write to a table and know I'm going to use the right compression algorithm when I look at that data later. And that's really powerful. So at Netflix, a couple of years ago, we moved over to Brotli compression. It's a compression library from Google, released, I think, slightly before Z Standard from Facebook. I still need to look into Z Standard and actually move our tables over. But anyway, Brotli compression gave us about a 20% decrease in total data volume across the board, which was a huge win for the scale of data that Netflix has in our data warehouse. But for some tables, we know that they got 20% larger. We know other tables got 40% smaller. So that's an average across all of our tables that we saved 20% on space. By putting the compression configuration for our Parquet files at the table level, we can have individual compressions set just for that table. So we can automate a process that goes and rewrites our data with 4 different compression algorithms and picks the winner and sets that on the table without users ever having to care. So this is a huge win because we're taking that thing that used to be a user level concern. If you want your data to be smaller, you have to go do some manual work and then set a property that you have to look up every time because no one ever remembers it. Well, in Iceberg, we want to move those concerns, those tuning options. We want to automate them and set them through the table. So having a table format library is really powerful because we can automate all that tuning configuration. And finally, I'm going to touch briefly on table layout. So this is what I was talking about when I said we either get a full table scan and users hate the performance, or users have to know the physical layout of our table and hate their lives because they have to take that into account. Well, in Iceberg, table layout is hidden. So we keep track of the relationships between a timestamp column and the date partition, so that when they filter on the timestamp, we know which dates to pull up, which files to read from the data. And that's really powerful, not just because a broad cross-section of users no longer has to care about the physical structure of the table. It means we can completely decouple the logical queries from the physical storage so that we can actually change the physical storage as we need to over time and not break any existing queries. Breaking existing queries gets people yelling at me, and I don't like that. So we can transparently fix the table layout from a data platform perspective. 3 years into a production table's lifetime, I can go say, hey, this should probably be hourly instead of daily partitioned. Just go flip a switch and fix it for a user. All right. So that's like the broad, set of goals and basically what Iceberg does. Next, I'm going to talk about why Hive is actually insufficient in the ways that I was sort of alluding to, and how Iceberg works to get around those things. All right. So first, I probably should have covered this earlier. What is a table format? What does that even mean? Well, in the early days, back before we realized we were rebuilding the databases, and we thought we were just going to be great distributed systems engineers, and who needs databases anymore anyway? We thought, hey, we kind of need a way to, get the amount of data that we're processing in parallel, but the amount of data down, because that's the best way to make our queries faster, which we didn't call queries at the time. So we thought, we'll just put all of our data in a directory structure, and then be able to go to the right directory based on the filters or the data that I need for a particular thing. Okay, so that's a great idea. Then we realized, well, we're doing way too much directory listing. Because just to find out what days are in a table and then what hours are in there took a really long time, right? So we'll just throw all of those partitions in a traditional database, and that'll be great. Then we can even push down the filters into that database, and things will go well. We'll still, keep everything in a directory though. Well, that's actually the state of Hive tables today. There are a few changes, tweaks that we've made over the years. Hive Acid is a thing, still works on this idea that we need to list directories to figure out what's in them, to figure out what data is in our table. So we're keeping state in essentially 2 places. First of all, we're keeping state in the metastore that tracks our partitions. And then second, we're keeping state in a file system that has no knowledge of what you're doing with it and absolutely no transaction support. So I can't write 2 files in my parallel, wonderful distributed system and tell the file system, hey, make those 2 files appear at once. And if I can't make those 2 files appear at once, then there's a split second of time when if I list that directory, I just get an incorrect result. Hence, my queries lie to me. So there's really nothing we can do about this besides lock, right? We can come up with a big fancy locking scheme, and that's what Hive did. But then it turns out that everyone wants fast queries. Why should Presto go to a Hive Metastore to ask, hey, can I read this table before it reads the table? So nothing ends up respecting this locking scheme, and we end up getting tables that lie to us. Oh, and it's even worse at scale because what we're still doing is listing one directory for every partition we're reading. So we have a ton of scale issues that gets even worse when you're talking about hitting S3. What about inconsistent listings and so on and so on. So yeah, that's a bad situation. So what Iceberg does is it tracks all the files in the table at some point in time. And we call that entire file listing a snapshot. So the idea is to transition atomically by pointing to snapshot 1, and then pointing to snapshot 2, and then pointing to snapshot 3. Each write produces a new complete snapshot, which is a list of all the data files in our table. So this is solving a number of problems. We no longer have to list anything. So inconsistent listing is gone. We no longer have to rename anything because we can make atomic changes to this file list. So it's not like we're trying to flip a switch and make those files all appear in as close a time period as possible in this directory. We actually get snapshot isolation. So a reader starts up if snapshot 2 is the current snapshot. A writer produces snapshot 3 shortly thereafter. Doesn't matter, they're completely isolated. So it works pretty well. In reality though, it's a bit more complicated. And I would love to, dive into that as well if that's where people want to head after this talk. But yeah, I've only got about 9 minutes left, so I'm gonna keep going. So I talked about some of the benefits of this. Oh, another one on my list, cost-based optimization metrics. So if you have state kept in a file system where users can just drop files into a directory and those are live and appear in your table, then keeping metrics for cost-based optimization of queries is a nightmare. You constantly have to rescan those files in order to have up-to-date information so that you can plan queries. So what Iceberg does is we put the metrics for each file into the manifest and the listing itself. So that way we have completely accurate information for every scan. So we're really hoping that all these cost-based optimizers and like Spark and Presto materialize in the next few months, because we're really excited to get good data to those cost-based optimizers and even take a step further beyond tables no longer lie to you and things like that, and get to a point where queries can reorder joins and things that are really going to matter to our users. All right, in our remaining time before questions, I'm going to go through a few performance numbers. So the use case that we're talking about here is a table of metrics. So all of our runtime systems in just about every microservice that runs at Netflix sends metrics once a minute to a system called Atlas. It runs a time series in-memory database to make these metrics available to us so that we can see at any time how our services are performing. Then it logs all of those after, I think, a 2-week period to our big data store so that we can do historical queries on those metrics. And the problem is that data set is absolutely huge. So we partition it by date, hour, Amazon region, and then we sort all of the data by the metric name. And we end up with 2.7 million files per month across 3,000 directories. So it's really, really expensive if you want to do a query across multiple days of this data. So we have a sample query here where I want to look up a whole bunch of metrics by tag and just grab the metric name and do a count distinct on the tags. That query in a Hive table took 10 minutes to plan. So 9.6 minutes of wall time just going out, getting that directory listing, listing all the files in those directories to figure out what data am I going to read. When we converted this metadata over to Iceberg, what we did is we did all of that listing at one time, and then we created snapshots and manifest files that list all of those files in the table so we can scan through it really quickly. So instead of having this O of n operation on the number of partitions we're reading, we have an O of 1 operation for the manifest file that we're scanning. We just go read a single file, scan through it, which we're really good at, and plan the splits that way. When we did that, we got that planning time down to 10 seconds, which was good. And then we still had 13 minutes of wall time actually running all of the tasks for that query. What we then did is we took all of the min-max stats from our Parquet files and aggregated them. Remember I said that we store this table based on metric name, and we sort it. So all of our tables, or sorry, all of the files in this table have a small range of metric names in them. And we should be able to skip most of the files. So believe it or not, that 13 minutes of wall time was actually spent sending out a Spark task that starts up, decides it has no data to process, and shuts down. It turns out we were doing 12 minutes of starting up, figuring out that we have nothing to process, and shutting down in total wall time. And that's absolutely massive because this was across a, I want to say 200 node Spark cluster. 200 executors where executors only have one core. So it was really 200, parallelism of 200. So we got the total wall time down to 42 seconds just by taking that metadata from the Parquet footers and putting it in our manifest files. So we can actually really optimize selective queries using Iceberg metadata. All right, and with that, I'm going to quickly mention that Iceberg is an open source project. It's Apache 2 licensed. We have a Spark 2.3 plugin. I have a branch for Spark 2.4 that I'll release soon. We have pig read-only support up on the GitHub project. We have planned Python support that's coming out soon. There's a PR for the Presto project, and we've also submitted it to the Apache incubator, and the vote is currently passing, so we'll see how that goes. So hopefully in another few weeks, we'll be talking about Apache Iceberg and integrating that into all of the Apache projects you guys know of.
Apache Iceberg incubating.
Apache Iceberg incubating, yes. So I think I've got 3 minutes left for questions. Anyone? All right.
So when you design the Netflix Iceberg, how different or what characteristics do you have to acquire from the traditional database storage engine? That's one thing.
Right. So the question is, what did we steal from traditional databases? Now, I'm not a database person because, like most people in the Hadoop space, I came from a distributed systems background and then was like, wait, databases matter? But we have things like keeping track of statistics for files. Iceberg hides all of the files under a table, so it actually behaves like a normal database table. We also use, I mentioned in, I think, like the second slide, that we have full support for schema evolution. That's based on using a unique ID for every column, so that when you delete a column and then add a column back with the same name, it knows that they're unique columns. It's not like, oh, hey, I already had an ID column. I'll just use the data from that. That can cause a lot of headaches for users. So things like those. I'm probably forgetting more things, but yeah, so we definitely tried to make sure we were doing some of those basic database things right. I think it's basically table stakes to get schema evolution done correctly, because users just are not going to care. If a rename of a table breaks everything, they're going to be like, your database is crap. There was another question. Yes?
What is the table layout scale? Does everybody choke point to one copy?
So scaling is actually pretty good because in terms of Metastore, we're not hitting a central endpoint. So what we do for metadata is we store them in JSON files that track manifests of files, and then we union all the files in those manifests. So for writing, we only ever write a new manifest or maybe edit a couple of them, and the bulk of the table stays the same across different snapshots. So that scales very well. Then the other thing that we do is the current metadata, this v1 or v2 or v3.json, that's just a pointer in a database somewhere. that's how we keep you know, a single current version of that table, and that always moves forward. So the database that tracks all of our tables is keeping track of one thing. All of the work is done optimistically in the driver or the planner, so that all of the writes happen basically they're distributed across our entire cluster, because drivers are distributed across our cluster. So all of the work is not just put on one central endpoint. Yes?
How do you clean up all your duplicated tables?
Oh, how do we clean up?
Or your files?
So basically clean up older snapshots?
Yes.
Or okay. So older snapshots are cleaned up by an expiration process that we have baked into the library. We have a service that basically starts up, gets the listing of all Iceberg tables, and runs that API. But you could easily just build one of those yourself, because everything logic-wise is in Iceberg. So it basically starts up, says, hey, what snapshots are older than my cutoff time, removes them and commits that, and then goes and cleans up all of the deleted files and manifests that are no longer used. More questions? Over here.
How do you do a table discovery? Like you would do in Hive show databases?
Yeah, so the thing I was talking about earlier that just points to this root of the basically metadata tree, that's a Hive Metastore. So we have our own Metastore implementation that we use for that. We have a implementation in the open source version that uses the Hive Metastore. So basically what you do is you create a Hive table for it and give it a bogus input format, put a table property in there that tells you where your current metadata file is, and then to change that, you atomically, well, sorry, not atomically, you lock that table, change it, make sure it was the version that you expected, and then unlock the table so that you get atomic changes in your versioning. Anyone else? Yeah, that's correct. We don't store any partitions in the Metastore. So the requirements on the Metastore are actually very, very light. Like I said, we just store this in a table property in what is basically a Hive Metastore, and then we make sure that that transitions atomically. Everything else is stored in this, this metadata JSON file. Now, we also realize that we've got our own Metastore. Many organizations have their own Metastores. No one really loves the Hive Metastore. So it's very easy to plug in something that does this, the job of this root metadata JSON file. So we basically pass an in-memory object and say, here's the version I think it is right now. Here's the version I want it to be. And then that API says, okay, I swapped them, or no, you have to try again. And then we have retries to minimize the write volume and things like that.
Is there any way to specify kind of like transaction isolation, or is everything basically just pre-fitted?
So there isn't really different isolation levels. It's just the snapshot isolation that you get from that. We do have single table transactions, which is basically batching up a number of changes and then only adjusting the pointer to the root metadata once. We've thought about some things for like cross-table transactions, but right now we really just want to roll out tables that work as a single table. We think that that's a good contribution and a good step forward for the community. And then we can work on those higher level issues.
You mentioned like min-max split to cut down on the number of files, not partitions, to limit the, I guess, like the wall time of the job. Is that limited to just certain fields, like what the partition field is, or is it possible to do that for all fields within that file? Like combinations of fields. I don't know if that's a basic execution engine.
Okay, so the question is really like, what metadata is stored along with every single data file that allows us to filter out all of the data files that we're not looking for. We actually keep data partitioned, just like in a Hive table. Only instead of taking that partition data and then putting it into a string and then putting that string in a database, we just keep a tuple of values so that we can really easily filter and efficiently filter on the values that are the same for all rows in that file. So we do partition filtering first of all to really get the bulk of the files out of the way. And then after that, we will use basically min-max stats if they're present for all of the remaining files and any column in there. Okay, well, cool. I think that's time. Thank you all for listening to me. I hope to see you joining the Apache Iceberg incubating community at some point. Thanks a lot.
Thank you.